The next frequently seen time complexity analysis expression is basically a logarithmic expression. So as part of this logarithmic time complexity, we will basically represent it using big O notation as order of log n. Here n is nothing but the size of the input that we have got. So one of the classic examples of logarithmic time complexity is basically a binary searching algorithm. Now, at this point of time, if you don't know what exactly binary searching algorithm, you don't worry. In the later modules, especially in the searching module, we will be talking about the binary searching algorithm, and whatever the time complexity analysis that we are doing here, we will do there as well. But here, since we are trying to understand each and every commonly seen time complexity expressions, I want to explain it here as well. But what exactly binary search does is, if we are given an array of values which are sorted, and if we are asked to search for a value, we can search that value effectively in the sorted array of values we have been given using binary searching effectively. So as part of this binary searching algorithm, what we will do is, whatever the array of values that we have been given, right, we will try to calculate the middle index, and we will eliminate the remaining half of the array if we have to continue the search in each and every iteration. For that, we will basically define the start index, end index, and we will try to calculate the middle. Now, as part of the binary searching algorithm, we will be running a loop as long as we have a non-overlapping start and end indexes that we have available in the array. Like I mentioned, at this point of time, don't worry about how the logistics of binary search will look like. Later on, we will be talking about the binary searching algorithm thoroughly. Okay, here in this while loop, we will basically try to calculate the middle index. Based on if the value at the middle index is matching with the value or not, we will eliminate the either left half or right half of the array, and we will still search in the remaining part of the array only by calculating the middle index in the remaining part of the array that could possibly contain the value that user has asked to search for. Okay, here if you see the while loop that we have written, right, in this while loop, in each and every iteration, we are eliminating the half of the array. So let's just assume that the input array that we have been given has n number of values. So if I run this while loop once, right, so the effective array size in which I need to search will have n by 2 number of values. If I run this while loop second time, the effective array will have only the half of the remaining half whatever we were using. So it will have n by 4. If we run the loop thrice, it will have n by 8 values. If you see the pattern we have here, right, if I run the loop for k number of times, right, ultimately I will have n by 2 power k elements left in the array. Why? If you observe here, it is nothing but n by 2. For the second iteration, it will be n by 2 power 2. And for the third iteration, it will be n by 2 power 3. So for the kth iteration, it will be n by 2 power k. Okay. Ultimately, we will reach a point where start and end index will be both pointing to only one element. That means we are left with the array or sub array that has only one element at the kth iteration. That's why n by 2 power k is equal to 1. That means n is equal to 2 power k. If we apply logarithmic here, log n is equal to log 2k. Here k is nothing but log n divided by log 2, which is nothing but log n. Okay, so that is the time complexity analysis of a logarithmic representation. So the simplest way of saying when your algorithm is going to take a logarithmic time complexity is basically because whenever you are trying to divide the input that you are getting into half, ultimately you will see the logarithmic time complexity. If we try to draw the time complexity graph that we have here, on the x-axis we will have array size, on the y-axis we will have the time taken. If we analyze and draw the graph for different values, the time complexity will look something like this. Here what you can do is, you can take for 0 units of time, you can do log 0, what is the value, for one input array size 1, what is the log 1, what is the value of log 2 for the input array size 2. Similarly, if you try to plot all those values in the graph will look something like this. Okay, so that is the logarithmic time complexity that we will often see on our algorithmic implementations. Okay, so the thumb rule that you have to remember here for logarithmic time complexity is, when we will get the logarithmic time complexity, whenever we are trying to divide the input values that we have got, we are eliminating the half of it and we are simply using the remaining half in each and every iteration. So that's when we will often see logarithmic time complexity. Now that we have completed the example which will give us the log n time complexity, let's look at the example which will basically give us the n log n time complexity. Here mathematically we will represent it as order of n log n using big O notation. Okay, so let's look at the sample program that we have written here. I have written a program called search in range using binary search, which will basically take the array of sorted values. Now our ultimate aim in this program is for finding all the values that are available from 0 till the length of the array. If at all, if we have that value available, we want to print it and we want to move on till the length of the array that we have gotten here. For that, as part of the first step, I am reading the length of the array. Obviously reading the length of the array, since it is an assignment operation and the length is directly available on the array, we will take constant amount of time. After that, we are executing a for loop. Here the for loop also we are executing from 0 till n, and in each and every step we are incrementing it by only 1. So let's just say if the array has 5 values, the for loop will get executed for 5 times. If at all, if it has 10 values, the for loop will get executed for 10 times. So basically the number of times the for loop is getting executed equal to the size of the array. And we know to calculate the time complexity of any iterative statement, the amount of time it consumes will be equal to the number of times it is running, right? So that step is clear. As a result, we know this for loop is running for n number of times. Internally, inside this for loop, we are using a binary search for finding if that value is available or not, right? And as part of the previous example, we have already understood binary search takes a time complexity of order of log n units of time. Since it is a separate function, if you remember one of the rule that I have mentioned, if at all, if we are using already existing implementations of already implemented functions, we have to take that function's time complexity into consideration as well. Since binary search is something that we have already implemented previously, I am assuming that since I am reusing it here, it will take a time complexity of order of log n units of time. So it will be order of log n. And after that, if at all, if the value is available at an index that binary search returns, we are simply printing it, right? So this printing will take constant amount of time only. Now to calculate the overall time complexity involved in this search in range using binary search function, let's just calculate. As part of the first step, what we will do, we will add all the statements that we have in the implementation. So first is calculating the size of the array, which is nothing but 1. So it will be 1 plus, and the for loop is getting executed for n times. So whatever the internal lines of code that is getting executed and is taking time, right, that will be log n plus 1. So the overall time complexity will be 1 plus n log n plus n. Here we can write it as n log n plus 1. Here the lower order terms are n and 1, that's why we will neglect it. As a result, the overall time complexity will be n log n. Here one thing that you have to understand is, since the for loop is getting executed n number of times, internally the statements that we have here are taking log n plus 1 units of time. As a result, the overall for loop's time complexity will be n into log n plus 1. As a result, after simplifying, the overall time complexity will be n log n. If at all, if we try to draw the values into the graph, right? On the x-axis we will take the size of the array, and on the y-axis we will take the time taken by the algorithm, and we will have values 1 2 3 4 5 6, right? Here also we will have 2 4 6 8 10 12 14, something like this, right? If at all, if you want to draw the graph with actual values, you can take the size of the array, and you can take, the time taken by the algorithm as well, by substituting that n value in this expression by using the calculator. You can find the n into log n value, and if you try to draw that graph, right, that graph will look something like this. Okay, it will be somewhere between order of n and order of n square. It will be lying somewhere in between. What do I mean by that is, this is order of n log n, right? For order of n graph, it will increase linearly with the time, right? So it will be n square will be something like this in the previous examples that we have seen. So n log n will be lying somewhere in between n square and n units of graph. Okay, so that is the n log n time complexity example and its pictorial graph representation.